let us recap. We talk about a situation where we are given a function f and given value c and want to see what is the limiting value of f as x approaches c. And so there's a situation where you can find the limiting value and you say, oh, whatever value you find, you say that's called L, just to be generic. So let me just use graphs to illustrate what two cases that we had seen. So suppose I have a C here, I have C here, the different cases, okay? Just bring down. Alright, so suppose I have a function f of x that goes like u like that, y equals f of c. Okay? Again, I'm just being generic. So in this case, I can see that when x approaches c from the left, so the function value goes like this. It's like traveling along a roller coaster. And when x approaches c from the right, and it goes like here. So you can see like the values, they meet together, and where they meet happens to be the value f at c. So this would be the L. So in this case, I'm gonna say the limit of the function when x approaches c, it equals fc. Again, I'm just being generic. I don't have a concrete defined function, so I cannot give you a number. But when we look at examples, we're gonna see numbers. So c is a number, f is a relation between the input variable and the output variable y. Okay, so f of c would then be a value. So L is a value. Okay, so again, when you see abstract symbols or notation, don't just immediately freak out. Just take a deep breath and be patient. Try to think through. I'm talking about the limit of a function. What is a function? Function is a relationship. So for example, f equals x squared. Okay, limit a function when x approaches a given value c. So both f and c should be given information, and from the given information, you look for what the limiting value is, if it exists. Okay, and we also saw another example that goes like this. Okay, let me say three cases. So y, x, c is here again, and the circle goes up like that. Okay, so here we have case number 2. This function is not defined at f of c. This function is not defined at x equal to c. So we don't have the notion f of c. So when x equals c, I do not have a corresponding value. However, that does not prevent me from finding the limit of f when x approaches c, because the limiting value is about the nearby behavior, not about what happens at f of c. So that's the key notion about limits. So then again, I look at what happens when x approaches c from the left hand side. So you can see it approaches this value, whatever it is. Okay, and for the right hand side, you can see that it also approaches this value. So it's the value where the empty dot is. So suppose we can find that value, then we have, in this case, limit of f of x as x equal to c equals the L. L is the value we find. Okay, so that's what it is. So we can still have the limiting value even though f of c is not defined. Okay, so that's case number 2. All right, case number 3. We have f of c defined here, so that's f of c, whatever it is. Okay, but our job here is not to find f of c. Our job here is to find what happens to the function value when x approaches c. So again, I look at what the behavior of the neighbors around c. So when I have x traveling from the left hand side approaching c, then the f of x like goes to this value. So it's the height where the empty dot is. And when x approaches c from the right, you can see like it drops, the function value drops down to where this empty circle is. So it goes here. So suppose this value is L, then we have the limit exists. Okay. However, this L is different from f of c. So f of c is defined over here, but the limiting value is not equal to the function value f of c. Okay. So here you see 3 possible cases. One is the limit exists and the limit L equals the function value, equals f of c. Second case, function f is not defined as c, so we cannot even talk about what f of c is. So this does not exist because it's an empty circle. However, you can see that for both the left hand side and the right hand side, they have the same behavior. They meet at this value L. So in this case, we still say the limit exists and the limiting value is equal to L. So here I'm not being super precise because I should have said the limiting value of f as x approaches c is equal to L. Okay, so when I write, I have to be very precise. I need to have the what and the where. Okay, because I'm just saying it, it's a bit too much to keep saying the same thing. But when I write, I have to have the what and the where. Okay, but I'm just trying to shorten the sentence. So I have to say like limiting value equals L. But when you write, you should always keep the what and the f. You shouldn't just say, oh, the limit equals L. No, that doesn't work. Okay, so make sure when you write, you have the correct form. All right, here is the last case for limit f exists. In this case, f of c is defined. It's like a jump, right? And when I look at the left hand side behavior and the right hand side behavior, you see that they meet, and that's all what matters. The limiting value of from the left hand side and limiting value from the right hand side, they meet. As long as they meet, then and it's finite. Then I say the limit of f as x approaches c exists and equals L, whatever height or the value L I find here. Okay, even though the L is different from f of c. Okay, so we have a situation, the limit equals L equals the function value. With a situation, the limit exists, but the function value is not defined. And with a situation, the limit exists and the limit is different from the function value. Okay, so from these three cases, you should see that the limit is about the nearby behavior of the C, not what happens at C. Okay, so that's the three cases you're gonna see for the situation the limit exists. Okay, so now let's look at the possible situations where the limit does not exist. So DNE stands for does not exist. The limit of f as x approaches c does not exist. And we have three situations. Now let's go look at. You have seen the first situation. So for example, if I have f of x defined as let's say actually let me do this. Let's say f of x is defined as 1 over x. Okay, so let's see what do we have. And we wanna look at the limit of f as x approach 0. Okay, so for this situation, you're gonna see, let's look. So in previous homework, one of the previous homework assignment, I told you that you should look up what the graph of y equal to 1 over x looks like. So when x is small but positive, it gets big. When x equals 1, 1 over 1 is equal to 1. And when x gets larger, the value gets smaller. Okay, so if x is negative, suppose I have x equal to -1. So 1 over -1, that's here. -1, -1. When x is equal to negative a half, so 1 over minus 1/2 equals 1 times, okay? So I'm gonna flip whatever I have down here. So minus 2 over 1. The 2 over 1 is just really just 2. So it's it's 1 times minus 2, so I get -2. Okay? So when x equals -1/2, the y value gives me -2, like that. Okay? And when x equals -2, then I get 1 over -2. So that's equal to -1/2. So where is 2? It's here. Okay, so -1/2. Okay, so putting this together, on the left hand side of 0, left hand side of x equal to 0, the graph looks like that. Alright, so now we have the graph. And we're looking at this limit. So I have the what that's located where? Where is here? X equal to 0. Okay, so once again, I don't care about f of 0. And in fact, f of 0 is not defined. So let's just remove this solid dot because it looks misleading. That's another one I meant. I just want to locate x equal to 0. Okay, so x equal to 0 is this, the origin. But f is not defined as 0. Alright, so let's take a look at it. If I have x approaches 0 from the right hand side, so going this direction, what happens to the function value? U goes all the way up. Okay, goes all the way up to positive infinity. If I have x approaches 0, but now from the left hand side, then you have the function value drops down to -infinity. So you see, compare this with the cases we have up here. They do not meet. They do not meet. So I have different left hand side behavior and right hand side behavior. So in this case, we will say this limit does not exist. Okay? But if I'm looking for the same function, if I'm looking at the limit of x, sorry, limit of 1 over x, so that's the f, I'm just writing it out where x approaches 1. Then if it's this is situation, so remember I kept saying the what and the where are important information. You cannot just skip it. Okay, so here I have the same function but different location. The 1 is over here, so this is where x equal to 1. Okay, so if I'm looking at the neighbors around 1, then you can see that the function values approaching from the left hand side of 1 goes to 1, and the right hand side also goes here. So this is, they meet at where f of 1 is. So you plug 1 to the function, this is 1 over 1, so the answer is 1. So you see, like, different locations would give you could give you different answers. So when x approaches 0, you get the limiting value does not exist. When the c here is 1, when x is approaching 1, then you have the limiting value equals 1. So both the what and the where are important. Okay. And unbounded behavior, what does that mean? That means the limit of f of x is equal to positive infinity or negative infinity, or it could be this situation that doesn't exist, but I mean, sorry, just the positive infinity or negative. Let's keep it simple. All right. So example. Let's say I'm trying to find limit of 1 over x squared, and x approaches 0. Alright, so let us plot this out. Sketch. So when x is equal to 1, 1 over 1 squared is equal to 1. When x is equal to a half, then I would have 1 over 1/2 squared. What's that? So it's 1 over 1/4. So when I have fraction over fraction or fraction downstairs, what I do is I have the numerator times the reciprocal of the denominator. So that's 4 over 1. So I get 4. Alright? If you forget about this formula, then you should add this to your formula sheet. Okay? So when you have a over b, a fraction or a number over another fraction, c over d. How do we simplify this? This is, I keep the numerator down there times the reciprocal of the denominator, so d over c. And then I end up having a times d over b times c. Okay? So if you don't remember this formula, you should add this to your formula sheet. And we get 4. So when x equals a half, the y value is like 4. Let's put it here. When x is equal to 2, so 1's here, 2's here, I have 1 over 2 squared, so that's 1/4. So that's let's put it down here. So we have the graph that looks like this. Okay. All right. And now what happens when x is negative? So let's say if I have negative 1 over here, then what is negative 1 squared? So after you square the negative number, the negative sign goes away. So negative 1 squared is the same as 1 squared. Negative a half squared is the same as a half squared. Okay, so negative a half squared is equal to a half squared, because you have negative times negative and it goes away. So when x equals negative a half, I still have 4. That's what it's like. When x equals minus 2 at the quarter, so you can see like it's like basically the same copy but with mirror symmetry like that. Okay. So now you see that both sides, when x approaches 0, they both go up as if they will meet up somewhere, I don't know, in the heaven, I don't know, but it's like all the way up to the point we cannot see. There's no limit, so it goes all the way up to infinity. So in this case, we will say that either we say the limit of 1 over x squared as x approaches 0 does not exist, or we say this equals infinity, to be just more specific. Okay, but bottom line, even if they meet, but both sides both go to positive infinity or negative infinity, we still consider the limiting value does not exist. But we can be a little more specific, say like, we not only know it does not exist, meaning it does not, both sides don't just approach a finite number that goes all the way to positive infinity or negative infinity, then we say it's unbounded behavior. The limiting value becomes unbounded, so it goes all the way up or all the way down. Okay, so this is a example. Oops. All right. And I'm going to erase this formula. So if you need more time, please pause the video, and I'm going to erase this. Oscillating behavior. This is an interesting situation. So most likely you are gonna see oscillating behavior in functions like sine of 1 over x and cosine of 1 over x, something like that. Okay. I will make another video discussing these functions, but for now, let me just plot it out for you. So roughly, the function goes like this. Okay, I'm not very precise, but it's like, it goes crazy when x approaches 0. So in this case, we have when x approaches 0, sine of 1 over x has oscillating behavior. So this is fine, but like all the way to the center, it goes crazy, so it does not exist. And the reason why it does not exist is because of this crazy oscillating behavior. Same for the other one. Cosine of 1 over x also does not exist, because you also see similar oscillating behavior. Okay, so it's just an example that's worth memorizing. And I think I'm gonna use a computer to do a plot out, so then you can see what happens. Okay, so a little recap. You see 3 situations where the limit of f as x approaches c exists. It could be the limit exists and the limiting value equals function value at c. It could be the limiting value exists but function is not defined as c. It could be the limiting value exists and function value is defined as well, however they do not agree. So the limiting value exists, but it's not the same as f of c. So that's for the situation where limit exists. and we have limit does not exist. So what we can see is a different left and right behavior. So for example, this one, we can see a situation like unbounded behavior, and the last is we can have a situation like we see oscillating behavior, and they appear in these two cases the most, like sine of 1 over x and cosine of 1 over x. I'll use a computer to do plot out for you. Okay, so here just need to memorize that we have an example that has a graph looks like this, or this looks like that. Okay, just roughly speaking. Okay, so 3 types for limiting value does not exist. 3 cases for limiting value exists. Okay, so there you go.